All right, picking up where we left off last time in section 3.5 with number 13. We're starting the section on the average cost, and we want to find the production level at which the average cost is a minimum. Remember, the average cost is C bar, which is C over X. So then we want to show that the marginal cost and the average cost are equal at this point, and we want to use a graphing utility. I have my graphing calculator open to graph the average cost function and verify our results. So let's start off with our cost function on number 13 is C, which is 2x squared plus 5x plus 18, which makes our C bar, our average cost, 2x plus 5 plus 18x to the negative first. And we're going to minimize this. So we're going to take the derivative, and I'm going to multiply by x squared over x squared. Set it equal to 0. So my numerator needs to be 0. And that means 2 times x squared minus 9 equals 0. 2 times x plus 3 times x minus 3 is equal to 0. X plus 3 equals 0, or x minus 3 equals to 0. X is equal to negative 3, which doesn't make any sense for production, or x is equal to 3, which probably is my answer. Let's verify that with C bar double prime is going to be positive 36 x to the negative third, or 36 over x to the third. So C bar double prime of 3 is 36 over 27 is 4 over 3, which is greater than 0, is all I care about. So since, or because, C bar double prime of 3 is greater than 0, C bar has a minimum at x is equal to 3 units. And I want to find what that is now. Haven't been asked to find that in the past, but C bar of 3 is going to be 2 times 3 plus 5 plus 18 times 3 to the negative first is 1/3. So this is 6 plus 5, and 3 goes into 18 6 times, is going to be 12 plus 5 is 17. And since that's a cost, that's in dollars. Now they want me to find dc dx as well, the derivative of the original cost function. And that is 4x plus 5. And they want me to evaluate that at x equals 3 as well, and show that 4 times 3 plus 5 is 12 plus 5 is also $17. Look at that. So at the minimum average cost, that will also equal the rate of change of the original cost function at that same x value. So the original function slope will be the same as the value of the average there. That's just something that they want you to know. So let's go ahead and graph the average cost function here, which would be 2 minus 18 uh, x to the negative second or divided by x squared. And I'm only really interested in the first quadrant, but I'm going to zoom 6. That didn't give me what I wanted. Oh, that was my C bar prime. I want 2x plus 5 plus 18 over x, that average cost function C bar. We can't see the other piece here, so I'm going to zoom out until I can see it. There it is, and I want to find that minimum value that's up there. Second calc minimum, and put a tick mark there, get on the other side of the minimum, somewhere over here, and put a tick mark, and come back somewhere close to the minimum. And we're going to confirm that that is as close as my calculator can get to 3 because it's dealing with pixels. So that's 317. That's right. That's what we got. And our way of doing it with calculus was much more precise in the way that the calculator is doing it. So let's go ahead and look now at number 14. Says that C is equal to x cubed minus 8x squared plus 20x. So C bar is going to be x squared minus 8x plus 20, and C bar prime is 2x minus 8. C bar double prime is going to be 2, which is always positive, so this is always going to be a minimum here for me. When I set this equal to 0 and solve, 2x equals 8, x equals 4, C bar double prime of 4 is equal to 2, which is greater than 0. So because C bar double prime of 4 is greater than 0, C bar has a local min at x equals 4 units. And I'm going to find what that is. C bar of 4 is going to be 4 squared minus 8 times 4 plus 20. 16 minus 32 plus 20 is a negative 16 plus 20 is 4, and that's dollars. So dollars per unit of production. I haven't said that, but that's dollars per unit. It's like a marginal cost, which is why I'm looking at my marginal cost here. dc dx is 3x squared minus 16x plus 20, and dc dx when x is equal to 4 is 3 times 4 squared is 16 minus 16 times 4 plus 20. I'm going to pull out the 16, and that's 3 minus 4 plus 20 is a negative 1 times 16 is a negative 16 plus 20 is $4 per unit. Again, is exactly what we had for C bar of 4. And I'm going to graph C bar, pick the right equation this time, x squared minus 8x plus 20. And second calc minimum, enter, get to the other side of it, enter, come back and make a guess. enter, and that is about 4, and that's 4. So 4 units of production, average cost per unit of 4. So that was number 14. Let's look at number 15. Fifteen asks us now to maximize profit, and it gives us a demand equation P equals to 80 minus 0.2x, and gives us a cost equation of 30 x plus 40. So my revenue equation is x times P is 80x minus 0.2x squared. And my profit equation is going to be R minus C is 80x minus 0.2x squared minus quantity 30x plus 40. Profit equation is 80x minus 0.2x squared minus 30x minus 40. So 80x minus 30x is 50x minus 0.2x squared minus 40. And then P prime is going to be 50 minus 0.4x. P double prime is negative 0.4. So whatever my critical number is, it's going to represent a maximum. Set that equal to 0. Negative 0.4x is equal to negative 50. Back to my home screen here. Negative 50 divided by negative 0.4 is 125 units. And so part A asks me at what price do I have a maximum profit. So let's just say because P double prime of 125 is less than 0. P has a maximum, has a local max at X equals to 125 units. So let's find the price that gets us to 125 units and maximizes profit. So little p of 125 is going to be 80 minus 0.2 times 125 is going to be 80 minus 0.2 times 125. It's going to be $55. So that was part A. Then part B asks us to, when the profit is maximized, what is the average cost per unit? So average cost per unit is going to be 30 plus 40 over X. And I want C bar of 125 units is 30 plus 40 over 125. 30 plus 40 over 125 is $30.32 per unit average cost. Let's look now at number 16. It's very similar. Sixteen says that I'm given a demand function. P is equal to 100 minus 0.5x. And the total cost function is C is equal to 50x plus 37.5. So my revenue function is XP. It's 100x minus 0.5x squared. And my profit function is R minus C is 100x minus 0.5x squared minus 50x plus 37.5 is 100x minus 0.5x squared minus 50x minus 37.5. So that would be 50x minus 0.5 x squared minus 37.5. And that's capital P for profit. P prime is 50 minus x, and P double prime, if I need it, is a -1, meaning that this will always represent a maximum profit. I set this equal to 0, x is equal to 50 units of production. So because P double prime of 50 is less than 0, P has a local max when x is equal to 50 units. Okay, so then we answer part A, which is the price that we set it at to maximize profit, which is little p of 50 will be 100 minus 0.5 times 50 is going to be half of 50 is 25. 25 away from 100 is $75. Then we want to know what the average cost will be at that point. So average cost will be 50 plus 37.5 over x, and C bar of 50 is going to be 50 plus 37.5 divided by 50. 50 plus 37.5 divided by 50 is $50.75 per unit of production. Let's look now at number 17. And this is also maximizing profit. We're given the profit equation, but we're given it in terms of the variable S for sales, minus 2s cubed plus 35s squared minus 100s plus 200, and S is measured in thousands of dollars, in thousands of dollars, and P is also in thousands of dollars. When we come back and answer the question, we need to pay attention to the fact that S is in thousands and P is in thousands. So we want to find the amount spent on advertising S that maximizes profit P. So S is not sales, it's the amount spent on on advertising. So P prime is negative 6s squared plus 70s minus 100, and find P double prime is going to be negative 12s plus 70. When I set that equal to 0, negative 12s equals negative 70 is going to be s equals 35/6 is where I switch. I'll be interested in that number in just a second. 35/6. So on let's see, on the left-hand side of that is 0, which would be positive and concave up. And anything to the left of 35/6 would represent a local minimum. And to the right of that, something like 6, because 36/6 is 6. So negative 72 plus 70 is a negative 2. That piece would be concave down, and on that piece would be a local max. So when we set this equal to 0, then we're going to want to factor out a negative 2. 3s squared minus 35s plus 50 is equal to 0. Negative 2 times, and in parentheses here, needs to be a 3s and an s. They need to break 50 down into its factors so that when I multiply here, I'm going to get 35. So I'm going to put a negative 10 here, gives me a negative 30, and a minus 5 there, gives me a negative 5. Altogether, that's a negative 35, and negative 5 and negative 10 multiplied to give me 50. So 3s minus 5 equals 0, or s minus 10 equals 0. 3s is equal to 5, s is equal to 5/3, or s is equal to 10. Now remember, I'm trying to maximize profit, so I want something that's to the right of 35/6. That's definitely s equals to 10. So there's a local max here. 5/3 is 1 2/3. That's to the left of 5 5/6. So there's a local min here that I'm not interested in. So I'm not interested in that number. And the maximum profit occurs when s equals 10, or $10,000. So that means if I spend $10,000 on advertising, that should maximize my profit. Now I've already found the second derivative and set it equal to 0. Just another step here. I want to actually do 6 into 35 here, go out a few places here, so that when 6 goes into 35, it's not quite 6, it's 5, just 30 with a difference of 5. And then 8 times 6 is 48 with a difference of 2. And then that is 3 goes into 3 times 6 is 18 with a difference of 2 again. And that 3 just repeats. So this represents 5,000. So my point of diminishing returns which is the point of inflection on the graph, happens at occurs when S equals 35/6, or approximately $5,833.33. 35/6 times 1,000 would be more exact. You could write that as a fraction, but we don't talk about dollars. In fractional amounts like that, we write them to the nearest cent. So let's go ahead and work on number 18 next, which is another similar problem with money spent on advertising. We want to find the amount that we spend on advertising that maximizes profit. We also want to find the point of diminishing returns. So our profit function is 0.1s to the third plus 6s squared plus 400. And so P prime is negative 0.3s squared plus 12s. And we're going to set that equal to 0. P double prime is equal to negative 0.6s plus 12. If I set that equal to 0, to help me find the point of diminishing returns later, 0.6s equals negative 12. Negative 12 divided by negative 0.6 is going to give me that s is equal to 20. And when I factor here, negative 3/10 s times s minus 12 divided by negative 0.3 is 40 equals 0. So negative 0.3s equals 0, or s minus 40 is equal to 0. S equals 0, S equals 40. So here's 20 for S double prime. To the left of that, like 0, I'll get something positive where I'm concave up over here. To the right of it, like 50, I will get a negative number like negative 18. All right, which means that anything to the right of 20 will represent a maximum. So there's a local max here, which is what I'm interested in. I'm not interested in the local min that is to the left of 20. So the maximum profit occurs when S equals 40, which is the same thing as $40,000. And then the point of diminishing returns occurs when S equals 20 or $20,000. Let's go ahead and look now at number 19. 19X asks us to maximize profit and says the cost per unit of producing an MP3 player is $90. So C bar equals 90. So C, which is equal to C over X. So C is equal to 90X. The manufacturer charges $150 per player for orders of $100 or less. So my price function is piecewise defined here. $150 for X is less than or equal to 100 units. And then to encourage larger orders, however, the manufacturer reduces the charge by 10 cents per player for orders in excess of 100 units. So 150 minus 10 cents per unit over 100 units when X is greater than 100. And I'm really only interested in that bottom piece because I know that that's probably where the profit is going to be maximized, is by selling large volume. So let's go ahead and continue reading the problem. For instance, an order of 101 players would be $149.90 per player. An order of 102 players would be $149.80 per player, and so on. Find the largest order the manufacturer should allow to obtain a maximum profit. Okay, so we're interested in the largest order, so we're interested in this second piece here. And so we've got our price function. Let's go ahead and simplify that. P is equal to 150 minus, and then a tenth of 100 is 10 minus 1/10 X, just distributing that 0.10 in, and so this is 150 minus 10 plus 0.10x is 140 plus 0.10x. I wrote this backwards. This is x minus 100 because we're already getting over 100 and we want to subtract 100 to find the difference there. So that was my fault. This is 0.10x minus 10 is going to be negative 0.10x plus 10 is 160 minus. There we go. Fix that. So now our revenue function, R is x times P, is 160x minus 0.10x squared. And that's really only good for x greater than or equal to 100, but our cost function, we have that here, is 90x. So our profit function is our revenue function minus our cost function is 160x minus 0.10x squared minus 90x is going to be 70x minus 0.10x squared. And our P prime is going to be 70 minus 0.20x. Our P double prime, if we need it, is going to be negative 0.20. So always negative, which means that my critical number that I'm about to find has to represent a maximum set equal to 0, negative 0.20x is equal to negative 70. Negative 70 divided by negative 0.20 is going to be X is 350 units of production. So now let's read the question, make sure we've answered it. Find the largest order the manufacturer should allow to obtain maximum profit. So we found that that's 350 units of production is what we want. All right, let's look now at number 20. Number 20 says that a real estate office handles a 50-unit apartment complex. When the rent is $580 a month, all units are occupied. So I want to write my point as XP because I want my demand function to be P equals a function of X here. So I have 50 units occupied when the price is set at $580 a month. And then they tell me that for every $40 that the price increases, we have one unit becomes vacant. So that means that I have 49 units occupied when the price is $620 a month. And I want to find the price that the real estate company should set the price per unit at to maximize their profit. We don't necessarily want to maximize occupancy because we might be losing out on profit if we set the price too low. So each occupied unit also requires an average of $45 per month to maintain, assuming you don't need to maintain a unit that's not occupied. So let's go ahead and figure out our price function here using our point slope form of our line. And I'm going to pick the easier number to deal with, 50 here. So 50 and 580, so P minus 580 is equal to, and then I want Y2 minus Y1 over X2 minus X1 for my slope, X minus 50. So this is P minus 580. 40 divided by negative 1 is a negative 40. X minus 50 is P minus 580 is a negative 40x plus 2000. And then we have P is equal to negative 40x plus 2580. So then that makes my revenue function R is equal to XP is a negative 40x squared plus 2580x. We have our cost function was given to us as $45 a month per unit that's occupied there. So profit function is going to be R minus C is negative 40x squared plus 2580x minus 45x is going to be negative 40x squared plus 2535x. That makes P prime equal to negative 80x plus 2535. And P double prime, should we need it, is negative 80. Always negative, meaning this critical number that I'm about to find has to represent maximum profit. So negative 80x is equal to negative 2535. Negative 2535 divided by negative 80 is a, so it comes up to be a decimal, right? So I get x is equal to 31.6875, and I can't sell a fraction of an apartment, right? I can't rent a fraction of an apartment, so I need to either rent 31 apartments or 32 apartments. So I'm going to have to check out, we'll need to inspect. X equals 31 and X equals 32 to see which gives a larger profit. But it has to be one of those answers that's right next to our optimal answer. Just our optimal answer can't actually happen here in real life. So let's go ahead and stick my profit function in here of negative 40x squared plus 2535x, and make sure your table settings are set so your independent variable is on ask. And let's check out what happens when x is 31. So P of 31 is going to be 41.45, and 32 is going to be 41.60. So 32 is better than 31. So 32 wins. So profit is maximized when 32 units are occupied. So now the question was, what rent should be charged to obtain a maximum profit? So now we need to go back to our price function, P. What should we set it at to get these 32 units occupied? So P of 32 is going to be negative 40 times 32 plus 2580. And I'll do that in my calculator. Negative 40 times 32 plus 2580 is, I should set my rent to be $1,300 a month. That was number 20. Okay. Look now at number 21. X asks us to maximize revenue, and it says that when a wholesaler sold a product at $40 per unit, 300 units were sold per week. After a price increase of $5, the average number of units sold dropped to 275 units per week. Assuming that the demand function is linear, what price unit will maximize weekly revenue? So let's go ahead and look at that. This will be P minus 40 is equal to 45 minus 40 over 275 minus 300 times x minus 300. It's going to be P minus 40 equals 5 over negative 25 times x minus 300 is P minus 40 equals negative 1/5 x plus 60. P equals 100 minus 1/5 x. So revenue is XP is 100x minus 1/5 x squared. And we want to maximize revenue. So R prime is going to be 100 minus 2/5 x. And R double prime, should I need it, is negative 2/5. So the critical number that I am about to find has to represent a maximum for R. So 2/5 x equals to 100, 2x is equal to 500, and x is equal to 250 units of production. Now to set the price, to make that happen, which is what we're asked to do, little p of 250 is equal to 100 minus 1/5 of 250 equal to 100 minus 50 is going to be a price point of $50 per unit. Go ahead and look at number 22. Very similar problem, but instead of trying to maximize revenue, we're trying to minimize cost here. So power station is on one side of the river that is 1/2 mile wide. Look at the picture in your textbook. I'm going to draw a picture for this one, but I'm going to read the problem to you. The power station is on one side of the river that is 1/2 mile wide, and a factory is 6 miles downstream on the other side of the river. It costs $18 per foot to run power lines over land, and it costs $25 per foot to run the power lines underwater. So we're going to look at the picture that's with this problem, and I'm going to do my best to draw it where we have this total. So here's the factory that I'll call F, and here's the power station that I'm going to call P, and that the distance straight across the river here, that this is the river here is this wide here is, if I drew that right, it's 1/2 mile wide. And there's a distance downstream that I want to go to this target point that I want to run my power lines underwater for a while, just directly to this point, and then run them across the land from there, because it's cheaper to run them across the land, but I want to optimize this. So I'm going to call this distance that I go downstream across from the power plant X. And since the total distance, the factory, is 6 miles downstream from a point directly across from the power plant, this distance is going to be 6 minus X. Okay, so hope that helps you. We'll be using a very similar picture in our next problem as well, just the numbers will be different. So we're going to use the Pythagorean theorem here, since this is a right angle, to say that the hypotenuse here is going to be x squared plus 0.5 squared. And if I want that distance all by itself instead of c squared, I want the hypotenuse is going to be the square root of that. So this distance here has to be the square root of x squared plus 0.5 squared. Half squared is a quarter, so I can just write that as 0.25 inside of the square root sign. So now that's the distance that I'm going to be in miles. That's the distance in miles that I am going to go underwater. But I need to change miles to feet because my price is in feet. So there's 5280 feet per mile. So I need to multiply by 5280. And I need to multiply by the cost per foot underwater, which is 25. Plus, I have a cost of $18 per foot and 50 to 80 feet in a mile times 6 minus X miles for my part that's going to be over land. So that's my total cost function that I want to minimize. So C is going to be one, 3, 2, 0, 0, 0 square root of x squared plus 0.25 plus 570,240 minus 95040x. Let me show you how I got those numbers. I used my calculator and I have it written down on my paper, but 25 times 5280 is 132,000. And then 18 times 2580 times 6 is 570,240. And then I have 18 times 2580 times -1 is negative 95040x. So now I want to take the derivative so I can minimize this cost. And that's going to be 132,000 times 1/2 times x squared plus 0.25 to the negative 1/2 times the derivative of the inside is 2x plus 0 for the derivative of that constant minus 9, 5, 0, 4, 0. This 2 cancels out with that 1/2, and I have c prime is 1, 3, 2, 0, 0, 0 x divided by the square root of x squared plus 0.25 minus 95040 over 1. Going to make a common denominator, x squared plus 0.25 square root of x squared plus 0.25. And I'm going to set that equal to 0. So c prime is going to be 1, 3, 2, 0, 0, 0 x. Actually, just need the numerators now. Minus 95040 square root of x squared plus 1/4 needs to be equal to 0. So let's take 1, 3, 2, 0, 0, 0 x. Move that to the other side, 95040 square root of x squared plus 1/4. And then let's go ahead and divide 1, 3, 2, 0, 0, 0 by 95040 just to make my numbers smaller and easier to deal with. Math answer to fraction. It's going to give me 25 over 18. So 25 over 18x is equal to the square root of x squared plus 0.25. So when I square both sides now to get rid of the square root, 25 squared is 625. 18 squared is 324. X squared plus, that's 1/4. So 625x squared is equal to 324x squared plus 324 divided by 4 is 81. 625 minus 324 is 301. X squared is equal to 81. X squared is equal to 81 over 301, or x is equal to plus or minus, which we need a positive distance, 9 over root 301 exactly, which is approximately 0.52 miles, because x was in miles. So to write a summary statement of what that means that the power line should run from the power station to a point across the river approximately 0.52 miles downstream, exactly 9/√301 miles downstream. Okay. So we've got another problem almost exactly like that now for number 24. Different context, basically the same setup for the problem. Number 24 says that an offshore oil well is 1 mile off the coast. So instead of a river, we have the ocean. I'm going to draw basically the same picture here that we have. This is 1 mile off the coast. This is the coastline. We want to pick a point somewhere down here that we're going to run pipeline instead of power lines now. And we have the oil platform, the oil well. So I'll put W for the oil well. And we have the refinery is going to be down here, is going to be capital R. And that's our point that is X miles downstream or down the coast, right? And there's the oil refinery is 2 miles down the coast from a point directly across from the oil well. So this is 2 minus X here. That's the portion that's going to be on land. So we have this distance here is going to be the square root of X squared plus 1. And that's going to be the amount that we're going to have to run underwater, under the ocean here. So laying pipe in the ocean is twice as expensive. It doesn't tell us what that price is. So I'll just say cost over land, we're going to call P dollars per, this is mile. Yeah, because we can pick our unit here. So P dollars per mile. And underwater is going to be twice as expensive. So 2 times P dollars per mile. So let's go ahead and say that our total cost function here is going to be 2P times that distance there plus P times this distance here. No conversion factor from miles to feet this time because we didn't have a price given to us in dollars per foot. We don't need to do that. So C is going to be equal to, I could just pull P out as a constant, 2 times the square root of X squared plus 1 plus 2 minus X. So when I take the derivative here, C prime, that P just sits out there and is 2 times X, 2 times 1/2 X squared plus 1 to the negative 1/2 times 2X plus 0 minus 1. And 2 times 1/2 will be 1. So this is C prime is P times 2X over square root of X squared plus 1 minus, and then that's going to be square root of X squared plus 1 over square root of X squared plus 1. So that means that I have, and I set this equal to 0, 2x minus the square root of x squared plus 1 is equal to 0, or the square root of x squared plus 1 is equal to 2x. X squared plus 1 is equal to 4x squared. And I have 3x squared is equal to 1, making x squared equal to 1 over 3, or x equal to the square root of 1 over 3, or 1 square root of 1 over the square root of 3, 1 over the square root of 3, which is the square root of 3 over 3 when I rationalize, and x is in miles. So that's going to be exactly what I want, but that's not something that I can measure very well. So I'm going to approximate it here. Say x is about, and we went to the nearest tenth of a mile, I believe, in the nearest hundredth of a mile in our previous problem. So let's do that again, is about 0.58 miles for x. And again, I could have found c double prime, and it would have always been positive, and we would have been finding a minimum cost here. So that means that, let me give myself a little bit of space to write this. The pipeline should run from the offshore oil well to a point on land approximately 0.58 miles down the coast, exactly square root of 3 over 3 miles down the coast. Okay. Let's look now at number 25. Just got two more problems, so I'm going to finish them up before I finish this video. I know we're getting close to we're a little over the 1 hour mark that I usually try and keep us to, but just bear with me as I finish these last two problems to finish this video before we move on to the next topic, which is very different. So number 25 says that we want to minimize cost where we have a speed v. It's important that it's speed, so it has to be positive. That's in miles per hour. That will minimize the cost of a 110-mile delivery trip. The cost per hour for fuel is given in C. So C is in dollars per hour. I know that's a rare unit for cost for fuel. We would normally say dollars per mile or something like that, but it's already calculated in dollars per hour. And W, the wages for the driver, are also in dollars per hour. So they made them the same kind of unit so we can easily add them together. We're going to need the formula here that distance is equal to rate times time. And we're going to need to know that our distance is 110 miles. So our fuel cost C is V squared over 310, and our driver's wages W is $13 an hour. So we have, let's find our time in hours. That's going to be D over R, which is going to be 110 miles divided by our speed that we go at is going to be V. So I'm going to take total cost, I'll call T, is going to be V squared over 310 times my time to get my dollars and cost for my fuel. So my time is 110 over V plus my driver's wages per hour, $13 an hour times 110 divided by V for the number of hours that he drove. And we'll reduce some fractions here and we'll get T is 11 over 31 V plus, and then that's going to give me 1430. 13 times 110 is 1430 over V for my total cost T. Since I already used the variable C, I'll just use T for my total cost. And T prime is going to be 11 over 31 minus 143 over V squared. Now T double prime, just to ensure that I'm getting a minimum total cost, is going to be -2 times -143 is going to be 286 over V cubed 286. I missed a 0 here. Yeah, I did. Got to put a 0 there. 2860 over V cubed. So that tells me that because V is always going to be positive, since we're talking about speed, T double prime will always be positive because V is always going to be positive. All right, so if we get a V that's negative here, we did something wrong, or there's something wrong with the problem. So let's go ahead. 11 over 31 equals 1430 over V squared. So 11 V squared equals 1430 times 31 is going to be 44,330. We're going to divide by 11 and we get V squared is equal to 4030. And then I want to take the square root of that to get V is just about 63.5 miles per hour. If I want to prove to myself that that is a minimum cost, stick it into T double prime, and T double prime of 63.5 is greater than 0. So T has a local min when V is approximately 63.5 miles per hour. That's what that tells me. Okay, we'll wrap up with number 26 here. It's exactly like number 25, but with some different numbers in it. So again, we have a distance of 110 miles. We're going to have D equals RT. So T is going to be D divided by R, which is going to be 110 divided by V. Our fuel cost is going to be given to us as V squared over 250 this time. And our W is going to be equal to 1850 per hour. Okay. So, and we're assuming there's no other costs other than wages and fuel. So our total cost is going to be V squared over 250 times 110 over V plus 1850 times 110 over V is going to give us T is 11 over 25 V plus, and then 18.5 times 110 is 2035 over V. And so T prime is 11 over 25 minus 2035 over V squared. T double prime is negative 2035 times negative 2 is 4070 over V cubed, which is going to be greater than 0 no matter what, because V is going to be positive. So whatever I find is going to definitely represent a local minimum. So this is 11 over 25 is equal to 2035 over V squared. 11 V squared is equal to 25 times 2035 is 50875. And I'm going to divide that by 11. And I get V squared is equal to 4625. And the square root of 4625 is V is about 68.0 miles per hour. So because T double prime of 68.0 is greater than 0, T has a local or relative min at approximately, or let's say when V is approximately 68.0 miles per hour. And that's it. We were not asked to find what that minimum cost was. If you want to find it, you can plug 68 into the total cost function to see what it would be. All right, that's it for this video. We'll come back and keep working on section 3.5 next time when we come back and talk about elasticity of demand. There's a whole bunch of problems on that. So we'll come back and talk about that in the next video. See you next time.